Today we're going to talk about motion diagrams. This is a way that we can represent an object's motion. So the three main topics we'll talk about are motion diagrams for an object going at a constant velocity, motion diagrams for an object that's slowing down, and motion diagrams for an object that's speeding up. So we'll start with constant velocity. Think of Francine. She's going to be running at a constant velocity of 10 meters per second. How can we represent her motion? We're going to start by representing it using a motion diagram. So a motion diagram is a visual representation of an object's motion. A dot is placed to represent the location of the object at each second. So this is an example of a motion diagram showing Francine moving at a constant velocity. Our first dot shows her position at the start at 0 seconds. After 1 second, this is her location at this dot. After 2 seconds, this is her location. After 3 seconds, this is her location. At 3 seconds, this is her location, and then so on, same distance each second. And at the very end, she's going to get to this location after 9 seconds. What you'll notice about this motion diagram is that it shows a constant velocity. She's the same distance apart after each second. So you can see that she's traveling the same distance between 0 and 1, and between 1 and 2, and between 2 and 3. Now we don't know from this picture how far apart these dots are. We just know the time between them, but we can see that this distance is the same as this distance. So we really are looking at how far they are relative to each other, not an actual measurement, at least on this motion diagram. So sometimes we have a motion diagram that uses dots, and they could be black or blue or any color you want. And those motion diagrams just show the dot to give you an idea of how far apart the objects are. You could also have a motion diagram that has arrows. So this is an example of the same motion diagram, but using velocity vectors. And that shows the direction of the motion. So it shows she's going to the right. It shows how long the arrow is, shows how fast she's going. And you can see that each arrow is the same distance. So we'll talk about velocity vectors later, but if you see a motion diagram like this, it's equivalent to the first one. We can also show motion using a position versus time graph or a velocity versus time graph. We're going to talk about these in a lot of detail later in the unit. Right now, I just want you to see them so you can see that they can relate to a motion diagram. So Francine's motion can be shown by this motion diagram. It can be shown by this motion diagram, or we can use a position time graph. This shows on the y-axis her location, on the x-axis the time. So at 0 seconds, her position is at 0. At 1 second, she's at 10 meters. At 2 seconds, she's at 20 meters. At 3 seconds, she's at 30 meters. So it's increasing the same distance each second, which is why it's a straight line. We'll go into that in a lot more detail later. We could also represent her motion with a velocity time graph, which shows velocity on the y-axis and time on the x-axis. And since she has a constant velocity, it's going to be continuously 10 meters per second on the y-axis. We also have acceleration versus time graphs, which we'll get to later. All right, so now we have Fred running to the right and slowing down as he goes. He's going to predict that this is his motion diagram right here, this first one. We have dots that are close together, and they're spreading further and further apart over time. So that's his prediction for his motion diagram. Francine is going to predict that his motion diagram looks like this. His dots are far apart, and they're getting closer and closer together over time. So we want to figure out which of these predictions correctly shows Fred slowing down. Pause the video and come up with an answer. What did you come up with? The answer is Francine is correct. You can number the dots 0, 1, 2, 3, and that'll help you get a better idea. We see that for the first second, Fred is traveling a greater distance per second than the last second, where he's traveling a smaller distance per second. So that means he has a greater velocity at the beginning, and then less velocity, and it's getting to smaller and smaller velocity at the end. Fred's prediction was incorrect because he has the beginning, he's traveling a short distance each second, and then he's getting faster. He's traveling a greater distance each second at the end. So the correct motion diagram of Fred slowing down is Francine's prediction. And it does help to number the dots. All right, now we have a picture over here, and this is a picture of me dropping a ball. It shows multiple images taken while a ball is being dropped. The time between images is the same. So you're going to draw a motion diagram for the ball. Let me actually just say, this photo I took using the Motion Shot app, which you can get for a smartphone. Here's the URL if you want to go there, and it allows you to record over time, and it'll overlay multiple pictures to give you a visual of how an object moves over time. So I want you to do a motion diagram for the ball while it is falling. So that means from the time it's in my hand and I drop it until it reaches the ground down here. You'll notice it's moving fast right here, so we have kind of blurry images. So when you get to the blurry images, you could just put a dot right in the center of the blurry image for your motion diagram. So first, draw a motion diagram for the ball while it's falling. Then I want you to identify, is it speeding up, slowing down, or traveling at a constant velocity? Then last, I want you to tell me, what do you think is happening at the bottom of the photo? So after it hits the ground, what's going on right here? Okay, so pause the video and answer these questions. All right, so here's my motion diagram. I've created a dot at 0 seconds, at 1 second, at 2 seconds. Well, it's actually not seconds. It depends on how quickly the camera goes. It's going to be less than a second, but the same time apart, whatever that time increment is. 3 seconds and 4 seconds. You'll notice that over time, the distance between the points is getting further apart, although it does slow down a little bit at the bottom, and that's because when the picture was taken, it had hit the ground, which is going to stop it and slow it down. So it's not going to travel quite as much distance before it hits the ground. But if it were from a higher height, it would continue to increase over time. So that's your motion diagram. It is speeding up. It's from the acceleration of gravity. Any object that's falling will accelerate. The distance between positions increases each second. At the bottom, it's bouncing. So it goes up and back down and up and back down. And there's a couple of interesting things to notice. First, it's traveling at a certain velocity, but it's slowing down as it moves upward. That's because gravity is continuing to pull it down. It comes to a stop at the peak of its bounce, and then it's going to speed up as it falls back down. So it travels a greater distance between points. Then it hits the ground again. When it hits the ground again, you can tell that it's lost energy because it comes back up at a speed that's less than the speed it came down at. So some of that energy actually goes into crushing the ball and into the ground. It goes back up, it slows down to a stop, and then it speeds up as it falls back down again. We're going to talk a lot about this kind of motion later. I think it's interesting to see in the picture, though. So as a summary, motion diagram is a visualization of an object's motion. A dot is shown for the location at each second. Constant velocity going to the right will look like this. The dots are equally spaced apart. Speeding up to the right will look like this. The dots are getting further and further apart as time goes on. And slowing down to the right will look like this, getting closer and closer together as time goes on. And that's all for today.